In this video, I will go over the homework that follows the lecture 1.3 called Integrating Exponential Functions. And this homework pretty much uses the following facts, which I hope you learn by watching this lecture. But here are a few facts that you need to know. So the integral of e to the x is e to the x plus c, and the integral of b to the x is 1 over ln of b to the x plus c. And of course, all the properties of integrals still hold. And that is, you can factor out the constant and split the sum or difference, and all the previous techniques of integration, such as substitution, can also be used in combination with one of these two facts or both. So let's take a look what's on the homework, and here's what the homework looks like. Let's start with the first problem, and we have an integral of -2 times 8 to the power -5x dx. And I guess before I do this homework, let me also show you a few simple extrapolations from the basic rules. So for example, if you are integrating e to the kx, we do that by linear substitution. So usually we do a quick sub. Let's say t is equal to kx, and then dt is equal to k dx, and therefore 1 over k dt is dx. So the integral becomes integral of e to the t 1 over k dt. So when you're integrating it, you can end up with 1 over k outside of the integral, then e to the t plus c, but t is kx. So for the same reason, I'm not going to write out the substitution, but I'm just going to write out this as a fact. If you have b to the power kx, following the same substitution, you're going to end up with 1 over k b to the power kx ln, well actually ln b will be here, so it's going to be 1 over k ln b to the power kx plus c. And this is what we're going to need in this problem, this bottom fact. So this integral, first we take out the constant -2. And now, if you want to use this substitution, here's the substitution for you to use. And you can work out all the details, as many as you need. And when you do indefinite integral, maybe that's what you would do. Maybe that's what I would do too. But right now, all I'm going to do is just use this fact. So we're going to have -2, 1 over -5 ln 8 to the power -5x plus c. And of course, we can simplify this. 2 over 5 ln 8 to the power -5x plus c is my answer. So let's try. 2 divided by 5 ln 8 times 8 to the power -5x, and let's not forget plus c. Yes, that's right. Keep it up. And if you look at the solutions, they actually do use the substitution, which is something I would recommend you doing, but eventually you're going to get tired of it, so you'll learn how to just not to write every single step. All right, next problem. It's a substitution, and I'm going to announce my substitution, so there's no confusion on what I'm doing here. And my substitution is going to be t equals negative 6x to the power 5, and dt therefore will be equal to negative, so I'm going to write it as negative 6x to the negative 5. So it's going to be negative 6 times negative 5, 30x to the power negative 6 dx. Therefore, dx is equal to 1 over 30 times x to the 6. So I'm just playing with exponents here. Dt. So when I do my substitution, and by the way, the constant negative 3 can go outside, and we have e to the power t dx, but dx is 1 over 30x to the 6 dt, and we have x to the 6 right over here, which gets cancelled. 130 comes out, so we have negative 1 over 10 integral e to the t dt. So the answer is negative 1 over 10 e to the t plus c, but instead of t, I'm going to write what t stands for, which is negative 6 over x to the power 5. That's the final answer. Next problem, the negative 2 goes outside. And this one can be tricky, but hopefully you can see right away that derivative of e to the x minus 1 is just e to the x, meaning we clearly have this pattern for substitution. T is equal to e to the x minus 1, so dt is equal to e to the x dx. And this time I'm not going to express dx in terms of dt, but I'm just going to rather point out this pattern that ex dx will be replaced with dt, and e to the x minus 1 will be replaced with t. And let's do that. So we have integral of, so e to the x and dx are connected and become dt, but we have t cubed dt. And the derivative of t cubed is 1/4 t to the 4 plus c. And the final answer we obtain after replacing t with what t stands for, which is e to the x minus 1. This is the final answer. Another problem that contains an exponential function. So we need to pass through the exponential function and to learn to identify larger patterns here. And here we have a standard substitution pattern. That is, we have a e raised to some power, so we have a function of square root of 5x, and we also have the derivative of square root of 5x. Where at? Well, let's find out what the derivative is. It's going to be 1 over 2 square root of 5x multiplied by the derivative of 5x, which is 5 dx. So now here I'm going to do this manipulation. I'm going to multiply by 2/5, so that way we can isolate this which will be replaced with this. So what we have here is -3 goes outside. We have integral of e to the power t, and everything else just becomes 2/5 dt. So now that we take out the 2/5, we get -6/5 integral of e to the t dt. So the final answer is, sorry, not yet. We're going to integrate this first, and then we're going to replace t with what t stands for. And that's the final answer. The square root. So it took us 4 problems to complete one of the 2 objectives, so probably to complete them all will take another 4 problems. We'll see. At some point, I was going to say that we're going to start expecting definite integrals, but remember the definite integrals are done. One approach is to find indefinite integral and then use the fundamental theorem of calculus. However, when you're doing a substitution, you may utilize another approach in which you switch the limits of integration during the substitution. So let me show you both, and then I'll just pick either one or another. So the first approach is we're going to focus on finding this indefinite integral first. So I'm going to take out 3, and I'm going to replace 4x plus 2 with a linear substitution. And dt is 4 dx, meaning dx is 1/4 dt, and the answer will be 3 integral e to the t 1/4 dt. So it's 3/4 integral e to the t dt, which is 3/4 e to the t plus c, which is 3/4 e to the power 4x plus 2 plus c. And now, because it was definite integral, I'm actually going to start writing the answer. So my solution is actually going to be 3/4 e to the power 4x plus 2 evaluated between -1 and 2. So 3/4 can be factored outside, and evaluating it at 2 gives me e to the 10, and evaluating it at -1 gives me e to the -2, and that's the answer. Now, alternatively, what I could have done is I could have continued writing the solution as this. So we have 3 integral from -1 to 2 e to the power 4x plus 2 dx. And here I'm going to give myself more room. And now I'm going to do substitution. So the substitution is the same, so nothing changes here. It's just how we write the answer. The order in which we write the solution changes a bit, but the solution itself is the same. But here, unlike in the previous method, I'm going to actually go ahead and change the limits of integration. So when x is equal to -1, t is equal to, and then I'm just going to go off how t is defined. So it's defined as 4x plus 2. So it's going to be 4 times -1 plus 2, which is -2. And when x equals 2, we get 4 times 2 plus 2, which is 10. So my new integral is 3. And now I'm going to put the limits for t from -2 to 10, e to the t 1/4 dt, and we have 3/4 e to the t. But this time, because I'm doing definite integral and I change the limits, I don't need to write plus c. I can just apply the fundamental theorem of calculus right away. So it's going to be 3/4 e to the 10 minus e to the -2, and that's, I believe, the same exact answer. So almost forgot to type the answer. 3/4 e to the power 10 minus e to the power -2. And I think Newton clearly prefers to change the limits of integration, which is the second method that I showed you. All right, moving along. Now that we know there are two methods, I'm just going to stick to the one that Newton does, and I think that would be my preferred method as well. In this case, we're going to, so let me rewrite this problem, right? So we have 3 times integral from 0 to 1, x, 3x squared, oops. We have x times e to the power 3x squared minus 4gx. I'm going to do substitution. T is equal to 3x squared minus 4. So dt is equal to 6x dx. So x dx is equal to 1/6 dt. And I'm going to change the limits. So when x is 0, t is 3 times 0 squared minus 4, so it's -4. And when x is 1, it's -1. So the integral now becomes 3 integral from -4 to -1. And we have 1/6 e to the t dt. So taking out 1/6, we get 1/2 e to the t, evaluated from -4 to -1. So the final answer is 1/2 e to the -1 minus e to the -4. The only reason I can think of not to do the change of limits right away is when you're not sure what the actual solution is like. So when you need to poke around before you start writing your solution, then I would recommend you to just do it as an indefinite integral. But once you figured out your path to the antiderivative, then change the limits, and that would be the most efficient way. Same thing. Let's take out 2. And we're going to do the same substitution. And again, why do we do this substitution? Because we clearly have a pattern here. We have e to the power g, and we have g prime here, and some coefficient in the front. And when you have a pattern like this, it literally screams, hey, do this substitution. The substitution should be whatever your g is. It should become your new variable. And me personally, I don't like using u as a variable. I don't like calling it u substitution. It's just a substitution. And the reason I don't like using u, because u and v are usually used for integration by parts. That's the reason. So here we're taking advantage of this pattern. Also changing the limits of integration, because the solution seems to be pretty straightforward. So when x is -2, t is equal to -8 times 3 is -24, plus 17 is -17. And when x is equal to 0, t is 7. So the final, not the final, but the new integral is from -17 to 7. We have 1/27 e to the t dt. And that's the final answer. If you want to check your work in an intelligent way, here's what I would suggest you do. You can type this function. Let's define this function. And here's the function. And what we're looking for when we do the integral is the area on the interval from -2 to 0. So in this case, we can see that the area is, if we just draw the domain out, so the domain is from -2 to 0, and what is this? Interesting. Like, so this is the region that we're talking about, and if we just eyeball it, we can see that this area is roughly equal to what? It's roughly a rectangle, right? I mean, there's a little bulge over here, but approximately it should be equal to base times height, and the height is 7. So the answer should be approximately, oh no, this +7 should be here. Okay, now it's a little hotter. Okay. Yeah, so now it's not as simple as I thought it would be. We can kind of eyeball the area by counting like this full squares. Each full square on the scale, it's going to be, this is what, 20. So each full square is, and this is 1/5. So each full square is 10. So if we count these full squares, we can kind of estimate the area. So let me count it this quick. 1, 2, 3, 4, 5, 6, 7, 8, 9. This counts like 10. Like this is 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. Let's say this one that's there. So 38, 40, 41, 42, 43, 44, 45, 46, 46 and a half, 47, 48, 49, 50, 51, 52, 53, 54, 55, 59, 60, roughly 60, 61, something like this, right? And let's plug this in. Our answer, e to the power 7 minus e to the power negative 17. And what did I say? 60, 61. I guess my calculations were a little too rough, so we're definitely not gonna find the area by eyeballing it. So the best way is to just find the integral from negative 2 to 0 of f of x dx, and this is how you know you got it wrong. Well, I mean, I got it wrong. What am I? Oh my god. Well, thank god I was checking the work, because I already see what I did wrong. The dt is actually 9, not 27. So this is 9. This should be 9. So instead of all of this 27s, it should be 9. And I guess my way of estimating those squares was way off for some reason. So 1 square represents 1/5. So 0.2 times 20. Oh boy. For some reason I thought it was 10 units, but it's clearly not 10. It's like 40 units or something. 40. It's 1/5 of 20, which is 4. So yeah, ignore my previous way of estimating. This is the way to check your answer. We clearly got the right answer. Because we were checking it before inputting, I have multiple mistakes here. So I'm glad I was checking my answer before inputting it into the answer box. So now I'm 100% sure I'm right. So spending a couple extra seconds, minutes to check your work before inputting the answer can save you more than a couple seconds in the future. So this is problem 8. And we have a definite integral from 1 to 2, 3x e to the 3x squared minus 1. Pause video for a second and try to guess which substitution am I going to use. It's a standard one. If you guessed this right, good job. Dt is equal to 6x dx. 1 over 6 dt is equal to x dx, and I'm going to change the limits. So from x to t, when x is 1, t is 2, and when x is 2, t is 11. So we got 3 integral from 2 to 11 of 1/6 e to the t dt. So antiderivative of e to the t is e to the t. And using the fundamental theorem of calculus, here's the final answer. As I showed you previously, you can check your work, but I'm fairly confident that this is the right answer. And we finished this homework. If you have any questions, feel free to reach out.